Okay, good morning. Welcome back. This is the continuation of our discussion in Mass 802, Algebraic Topology. So yesterday we have looked at two operations on spaces. That is the disjoint union and quotient spaces. So we have seen a number of examples of quotient spaces. Today we are going to look at the fourth operation on spaces, or construction of new spaces out of the existing ones. And this is a special type of quotient space, which is called adjunction space. So or it is called attaching spaces. So you can take a space and attach to another space to construct a new space. This is the intuition. So the way to do it, it's actually still a quotient space, but you assume you have two topological spaces. So let this be, suppose these are topological spaces. And that A is a closed subset. Well, closed subset, it can be regarded as a subspace with the subspace topology of the space X. And then if we have a map from A into Y, so you think of this as a subspace, and then you have a continuous map. Between the two topological spaces. Then we define an equivalence relation. You remember from yesterday, we define quotient space via an equivalence relation. So you define an equivalence relation tilde to be the one generated by, so but on, you define it on what? On X union Y. You remember this? This is a space. It's a disjoint product space. You can always find this disjoint product space. So on this space, or on the disjoint union of X and Y, you define an equivalence relation to be the one generated by A is related to f of A for all A in X in A. So only element of A. Every other member here is related to itself, and then members of A will relate to their image in Y under this continuous mapping. I hope that is clear. Okay? And vice versa. So you just use that to generate an equivalence relation. So meaning the image of a point in X in A will be related to itself, and that point will relate. When what we mean by generation, it means you use this as the basis to generate an equivalence relation. So point in A along with their images in Y will constitute one equivalent class, and the remaining point in the complement of such will be will consist of singleton equivalent classes because they relate only to themselves. So this is what we mean by that. Once you have this equivalence relation, then you can think of defining a quotient space by this equivalence relation. Okay, so you generate a quotient topology using this equivalence relation induced by the relation. Okay, so then, so with this, so we define this equivalence relation and call the resulting quotient space. X by tilde. You know, we have looked at many examples of this kind of construction. So we call this quotient space the adjunction space. Formed by attaching the space X to Y via F or along F. Let's say along F. And this mapping F is called, so the adjunction space formed by attaching X to Y along F. And the map F is called an attaching map. An attaching map. So we call it attaching map. That continuous mapping, because it's the one that you use to generate the equivalence relation. It's like you are using the mapping to paste the space Y, but along this subset A, okay, to it. And this adjunction space is denoted by, so the notation actually is to pronounce the attaching map. The adjunction space is denoted by X union F Y. So actually the adjunction space of obtained by attaching X to Y along F, okay? Because all you require is the mapping F and then the subset. Well, the subset is always there, but it should be a mapping from the subset, okay?
Will the mapping be continuous?
Yeah, continuous. In fact, almost all mappings must be continuous. Continuity in the sense that, you know, if it is not continuous, you will see the danger because the pasting may not be possible. So we want the image. If the set is closed, you can see that this is a closed subset. And so the image should also be closed in here. And it can only happen under, for certain, it can only happen under a continuous what? Map. Because if F is continuous, the image over there will also be continuous. So this is it. So you can imagine this adjunction space as a, so let me give you example as, for example, you can think of this as maybe having X to be the cylinder. The cylinder is S1 cross I. You see, even though we saw one way to think of cylinder yesterday as a quotient space, but it's not okay. That is, if you identify the two opposite edges of a square, you form a cylinder. Okay, so if you think of having a cylinder like this, so cylinder is this one, okay, but then at the bottom of the cylinder, this boundary of the cylinder is the cycle. So you can take that to be your A. And then, so if X is this, and the Y, A to be the cycle, imagine to be a subset of X, that boundary of the one of the other boundaries of the cylinder. And then you also take Y to be any topological space, any space, can be of any sort. So if Y is any space down here, but then you have a mapping from the cylinder down to, from the cycle, so from A down to here. And a cycle is closed, so we chose the subset to be closed because that's the condition attached there. So the image will be some subset over here. Okay, so what you will do is to say point along here, every point here, A, on the cycle will be identified with its image. So point here are mapped to point on the cycle, on the space Y. So then you can imagine that the identification is you are gluing this cycle on the image, to the image of the cycle inside the space Y. And so the resulting space, adjunction space, X, Y along F will be something like this. You think of so as if you are kind of so you attach that edge, but it doesn't have to come as a cycle, because the image may not necessarily be a cycle there, but whatever it is going to be a closed subset of Y, so you can attach it. So point here will be identified with the point in Y that are their images. So this is the resulting space, and this will be the space you obtain. So I can always take a space and then try to, if you have a mapping which is continuous from a closed subset of the space into the space down here, I can glue it together along the closed subset. Once you glue, then you create a new space. And that space is what is called the adjunction space, or the space obtained by attaching this one on this along that function, that continuous mapping. So this is this kind of adjunction space. It's something that we are going to be looking at. The next one that I want to mention is the connected sum. And before I say about the connected sum, there is also what we call the wedge product or wedge sum. Wedged sum. So this wedge sum is just like, it's an also instance of quotient space. So you have two spaces, X and Y, then you pick a point in X and a point in Y, and then generate an equivalence relation by saying X is related to Y. You generate, so only X is related to Y, and then you identify these 2 points together. And so the on the disjoint union, that is X, you define the quotient space, using this. So once you do this, you get the wage product or wage sum donated by this. So you can think of this like for example, if you take a cycle and you identify a point of the cycle, S1, and then you take another cycle and you identify a point, and then you can glue the 2 points together. So this point is equivalent to that one, then so you identify them together, and then you have a new space. The wage of this will result to a new space where this point of the cycle are identified. So this is the wage of S1 and S2 cycles. And this space now is not what? It's not homeomorphic to the cycle. It's a new space we created. In fact, it's not even a manifold. The cycle is a manifold, but when you form the wage, you don't get a manifold. So in fact, you can have a number of collection of spaces whatsoever and identify one point of the spaces, and then you glue all the points together, 1 point coming from each space, and then you get them all together. Like you can take the cylinder and take a cycle and identify this point and glue them together along there. So you just form a new space by gluing a cycle on here, or you can take a cycle and put it here. It gives you a new space. I hope it's okay. So this is the wage sum. But then we can still another special case of quotient space, the connected sum. So connected sum and the process is called surgery on spaces, that is topological spaces. Like so the way you do this is to take 2n manifold, for example. You can do it with any number, n dimensional topological space, but we assume we are working with manifolds. So let me say manifolds, and let's say M1 and M2, or X and Y, and Y, n manifold. You remember what this is? These are manifolds of dimension n. So we are talking about a topological space that is second countable, locally Euclidean of dimension n, and also Hausdorff. Okay, we define this in our first lecture, in the introductory class. So if you have this n manifolds, you can, so it can be like you have a sphere and another sphere like this, or yeah, you can think of having a sphere, like you have a sphere. You remember a sphere is two-dimensional. So, and you take, so this is S2, this may be my X, then you have a torus. A torus is also two-dimensional. And this will be my Y, so T2. So what you will do is both of these are closed manifolds. They don't have, there is no boundary. So you can cut a disk out of this. That is a ball of dimension 2. So if you remove a disk, B2, you can also cut a disk from here, B2. And then you have created boundaries for these spaces. You know, once you remove a disk, it is no longer closed. So you have created a boundary. So what you have, so if we now, so it will be true that this boundary and that boundary are homeomorphic. You know, this space without the ball of dimension 2 and that space without the ball of dimension 2 are also homeomorphic. That is, you can choose any homeomorphism from, so we can take a homeomorphism from X minus the a ball of dimension n, because this is a manifold of dimension. I can remove a ball of dimension n into y minus a ball of dimension n. So there will be homeomorphism, not homeomorphism between the two spaces because they may not be homeomorphic, for example, these spaces, but between the boundaries. The boundaries of the spaces on removing a ball of dimension 2 will be homeomorphic. Such, because this boundary will be homeomorphic to a sphere of dimension n minus 1. And this will be homeomorphic to a sphere of dimension n minus 1 also. So such a homeomorphism exists. So if you take any such homeomorphism, you use that homeomorphism to define an adjunction. You define an adjunction space because it means you have a continuous map from a subset of this. That boundary is a subset of this into that one. I hope it's okay. So you think of this as your space X, and then the boundary you can take as your A, our definition of the adjunction, and this one as our D. So which means with this, I can define the space that is the adjunction space X minus Bn union along F. So y minus what? Bn. It's not. Okay? This adjunction space, which will be equal to, let me write it up here. Over there, I mean. So X minus what? The boundary Bn, you remove a ball of dimension because this is a topological a manifold of dimension. So you take y minus Bn, and this will be the quotient space. Remember how we define the adjunction space? So you form the joint union of these two. So it is actually X minus Bn union, the disjoint union of y minus what? Bn, quotient, the equivalence relation. And the equivalence relation is defined in this way by identifying, so every point on the boundary here will be identified with the corresponding image over there, over F. So it's actually via this homeomorphism. So the boundary is identified. So actually via that mapping. So you identify the boundary of the y x minus Bn identified with y minus what? Bn. So this adjunction space is what we call the connected sum of y and x, or x and y. Okay, the connected sum of the two spaces is denoted by x hash m. So connected sum is denoted by hash. Okay, the process of forming
looking like a live version.
A connected sum, yes, is called performing surgery on manifolds. So what happened when you do it? When you do the connected sum of a sphere and sphere, what will be the connected sum of two spheres? Or we can start with a cycle. So what is the connected sum of a cycle with another cycle? This will be still a cycle, because if you have a cycle and another cycle and you remove, this is one dimensional, is one dimensional, go. So if you create boundary, because this is closed surface, okay, so I think over here we should two closed. When you say closed without boundary, okay, so we assume closed manifolds without boundary. So if you have this manifold and that manifold, and then you remove an interval, that is B1, and you remove B1 over here, then you have created boundary. Then you now identify there is homeomorphism, that F. So this point will be identified with this, and that point will be identified with this. So which means if you do the connected sum, you are getting something homeomorphic to what? What you get is this one, the cycle, but then you identify this, another cycle. But this is still a cycle, okay? So the connected sum of a cycle and itself is a cycle. What of if you take a sphere, like I took a sphere of n dimension, so let's say a sphere, and you take a torus. So you have the sphere, and you remove a ball, and you have the torus, you remove a ball, and then you stitch along these ones. So what do you get? You still get the torus, because this will be this one. So it will be like the sphere is pushed inside. You know, you stitch along this boundary, you glue these boundaries together. But once you do the gluing, it's like this sphere without the ball, the disc is just isomorphic to a disc. So it's still a disc you are attaching there. So it's like you are removing a disc and putting the disc back. So this is still the torus. So it's still the torus. So when you do this, you still get the torus. In fact, if you take any n-dimensional sphere and an m-dimensional closed manifold, and you take the connected sum with any m-dimensional manifold, you still get the manifold back. Okay, so it's like the sphere is acting like the identity of this operation, this connected sum. Okay, so this is it. So let me just define for one more class of manifolds, which we call, which is very important in the theory, and that is the Riemann surface. So the Riemann surface of genus. Genus is actually the number of holes included in the surface. So the Riemann surface of genus G is defined to be this space. That is the connected sum of torus with itself, G times. When you take the connected sum of a torus, G times, you get a space that is called Riemann surface. Like if you take T2 with T2, this will be like you are having a torus and another torus, and then you think of removing the disk and connecting it together. And then the resulting space will be this one. So when you join it together, you have a torus with two holes. Right. And in general, this connected sum, when you think of having G copies of a torus, it is going to be this space. It's like you are having a torus with G holes. Okay? So that's it. All right. So the last thing I will say in this, under this section of constructing new spaces, this is another way to build up spaces, new topological spaces from the existing one, and this is the one that is called cell complexes. They are very important. We are going to talk about cell complexes later on when we are going to introduce homology groups. So we will look at a special class of cell complexes called simplicial complexes. Okay, but I think it's good to introduce those at this point because we are talking about identification spaces. So cell complexes or cell complex is also called, so this is a generalization of the quotient space. It's a generalization of the identification space. You remember when we constructed the torus as an identification space, we look at this square or rectangle, and then we identify the edges straight in the same direction. So first of all, we folded this to form a cylinder, and then we fold it like this. And at the end of the day, we obtain a torus. So you can think of this torus because when you do the identification, all of these points were identified to be one point at the end of the day. So the first time you put this point, and then later on you fold it like this. So you can imagine this is your A, and you had, and this is the B. Okay? This surface, that is T2, so it can also be constructed in this way. You can start by looking at an octagon, that is how many side? 8, the octagon. And then you can now identify the edges, the vertices or the edges. So this edge can be identified with this edge. So when you glue them together, like identification space, and then you also identify this with this, because if you glue this together, you glue these ones together, and then you have C over here, and it will be identified with this C, and that will be D to be identified with this in the same direction, not opposite direction. Okay? By the time you do this identification, what you will have is that type of surface. That is a torus with two holes. And then it's as if you are starting with a single point, and then attaching an edge A and another edge D, and then you have from here this edge B, and you have this edge C. So this is an identification. In fact, almost these spaces, many of the interesting topological spaces can be constructed in this way. So you see, the way you think of it is like you are, for example, let me take this one. Like you are starting with a single point, and then you attach to the single point edges, and then you attach edges like that. This is your B. And then what you do is to attach a two-dimensional disk to these edges to close it. So it's like you close the disk with a two-dimensional disk. Okay, so so it's like you are developing this surface using points and then edges, and then you are now putting surfaces, that is a disk of two dimension. So this is a way of thinking of building up. So you can think of it as if you are constructing it from a discrete set of elements. Like for example, if you want to construct this space, this particular space, you remember this space, this inside is included. So, and that is how you do. So you can think of it as you started with 4 points, and then, but these 4 points, you know, they are, this is a ball of dimension 0. Yeah. And then you attach balls of dimension 1. Then you have this, this is it, this is a graph, this is a square. I mean, inside, without the interior. And then you can now attach the interior, that is an open disk, to it. And then you have what? D2. I hope it's okay. So you think of building spaces in this way. In fact, even the sphere, it can be built up like this. Like you can think of having 2 points, and then you now attach edges to the points, and then you now bring an open disk, close the sphere. So it's like you have a hemisphere, and then you attach another open disk at the top to close the top, and this will be a sphere. What you get is isomorphic to a sphere. I hope it's okay. So formally, you can define this construction, this type of spaces that can be built up like this are what we call cell complexes. So you can formally define cell complex in this way. But before then, we have to define what we call an N cell. So an n cell, for n and n being open n cell, is any topological space, n being a natural number, can be 0, greater or equal to 0. Is any topological space that is homeomorphic to an open ball. Open ball is Bn minus the boundary. We don't have any standard notation for the open ball. Bn is the closed ball, but without the boundary. And this is in the Euclidean space, the way we define the unit closed ball, Bn. So if you remove the boundary, you have open ball. So any topological space that is homeomorphic to this is called an N cell. Okay? An open N cell, and a closed N cell is a space, topological space, that is homeomorphic to this time around an N ball. So any space homeomorphic to N ball is a closed N cell. Okay? Sometimes we just say an N cell. So definition. A cell complex sometimes called CW complex, is a topological space that is constructed in the following way. So constructed by the following procedure. So the first step in constructing a cell complex is to have what is called zero skeleton. So you start with zero skeleton. What is zero skeleton? X0, it means just a discrete set of points. So you just start with the zero skeleton, like a discrete set of points, like this. Okay? Whose point or element are zero cells. So zero cells will be any space that is homeomorphic to closed zero cells. Well, if we say zero cells here, we mean closed zero cells. So any space that is homeomorphic to a ball of dimension 0. A ball of dimension 0 will be just points. I hope it's okay. So just a discrete set of points like this. Okay? And then the second step is to inductively form the n skeleton xn from an already constructed n minus 1 skeleton. So you form an n skeleton by using attaching open n cells en alpha via an attaching map. They are attaching maps. So this is a family of mapping. So what you do, you just take, you keep attaching open n cells, attaching maps. Okay, sorry. Via attaching maps. Okay. The mappings will look like there are mappings from, so these attaching mappings are phi alpha, which is a map from the boundary of a ball of dimension n into the skeleton. You know, if you are talking about an open n cell, it is any topological space that is homeomorphic to what? An open n ball. Okay? It's called an open n cell. So the boundary of that, this particular open n cell is homeomorphic to the boundary of the open, or of the ball, a closed ball of dimension n. I hope it's okay. So you use such homeomorphism to attach. It's like you are constructing this space as the adjunction space using that homomorphism you know, to do the pasting. So that is what is happening. So that is, we are saying that this space xn is nothing but the adjunction space obtained from here, well, using, that is obtained by attaching the space xn minus 1, or the ball. So maybe I should write it, well, by attaching the ball of dimension n to the space, to this already constructed n minus 1 skeleton, but via phi alpha. Okay? So this is what you will do. So if you take a dimension, because you have 0 skeleton already, the discrete set, you already have it, then you now want to attach open 1 balls. Okay? So these open 1 balls, you just attach them because they are going to be the open intervals, you know, to connect these vertices. So once you attach, this is the boundary of the open ball, you know, into there. So you attach vertices like this. You can attach as many as you can, as you want to attach, but once you do that, you obtain a 1 skeleton. And this 1 skeleton is just a graph. Okay? And you can stop there and say this is your complex. So this is a cell complex of dimension 1. So this will be a cell complex, but you can stop at, and then but you can go ahead and start attaching, constructing X2. That is the 2 skeleton in the next step, because you are doing it inductively by attaching to this. At the boundary, you attach a closed and open 2 ball, that is open disk. So what you do is to attach some open disks like this. Maybe you have an axis like this, then you can still attach another open disk. So you see you are developing space. And then at the boundary of the open disk, you can still attach balls of dimension 3. You keep developing this space like this. So this is how you do it. But then once that is done, the resulting space X, which is equal to the union of all this skeleton. For any n, you can take n up to infinity. If you stop at any finite number of n, then you have a finite dimensional complex. So the resulting space is what is called a cell complex. So you declare X to be this, and then X is given the weak topology. So weak topology in the sense that, so that is to say, a subset A of X is open if and only if it is the intersection with Xn. So at any stage, the intersection of this with the, with any n skeleton is open for all n. So with respect to this topology, you can still consider this one because this space is nothing but an adjunction space. So it's a quotient space. So you can think of it with the quotient topology, or you can give it the weak topology in this sense. So if you give it the weak topology, this is called it's called CW complex. But generally, it is a cell complex. Okay? So, I have already given you some examples of a cell complex. You can always do it. How do you form a cycle? A cycle is just you start with a point, that is your 0 skeleton, and then you put an open n cell, 1 cell. You put a 1 cell, so that is you attach a curve, a loop. So you have a cycle. I hope it's okay. So you can construct a cycle like this. And you can also construct a disk like this. If you form a loop, you have the X1. This is the 1 skeleton. Then you can now develop the next stage by attaching an open disk inside the loop. I hope it's okay. Or you start with 2 points, and then you attach 2 1 balls, 1 cells, and then you also put an open cell in between. All this you can think of constructing a disk like this, stage by stage. So most of these spaces can be constructed in this way. So in fact, you can You can construct so many other spaces that we have not seen so far in this way. But then we are going to actually define another special kind of cell complexes. It's called simplicial complexes, where you are using convex sets in Euclidean spaces to develop the cells, to develop the cell complex. And such are called simplicial complexes. So we are going to look at it later on. I think we will stop here. Next time we are going to start talking about homotopy and homotopy equivalence. Thank you very much.